So coming over here, we have a fusion design. This is a very simple design I have here. It's just a triangle, and I've really simplified it in many ways, such as I had pins going along through here, so it was pinned to the piece of wood. And to simplify the modeling even more, I removed those pins and I just assumed one of them is going to be fixed. So when you're doing your simulation, you have your fixed points. You could make pin joints down here, which I did, and I put a weight over here. I made my contacts, which were just where these pins were overlapping over here. I did my mesh and I did a result. So if we look at my results over here, we can see over here this is the bending of this part of the lifting device. Now, because this is fixed over here, in real life it's probably not going to be this way. This is going to rotate, but because it's fixed, it's shooting off at that particular angle, so that's why it makes like this S-looking shape, because it has to keep this original angle. But over here, because this is a pin, this one was able to rotate. That's why this is a solid curve. And even though this looks terrible in displacement, it's only 1.4 millimeters, which is, quite small. But if we get it off displacement and we look at things such as stress, we can see that we have quite a large amount of stress over here at 351 megapascals. So where this pop rivet is, it's probably going to pop or break. And then when we look at our factor of safety, we can see a lot of danger happening over here where all these loads are concentrated, which kind of makes sense. But this over here is what we call a static stress, where it's just trying to solve these products based on how it thinks it would work in the real world. So on a purely mathematical basis is how it's doing these products. So if you want to think, if there was like a rod of metal, so like think about a 5 centimeter by 5 millimeter cylinder of metal. If you put a force down on that piece of metal, it would assume that it's going to keep going down until it gets to zero length. Or if you imagine you have a 30 centimeter metal ruler and it's perfectly straight as you buy it, and you put it on your table and you push down on that metal ruler, it's going to assume that it's going to act as a spring, and it's eventually going to go down to a very, very small size. But we know when we do that in the real world and we try to push down a metal ruler, it doesn't work that way. It bends to the side. This is what we call buckling. So we have to do a different case study when we care about buckling, because we have to assume that failure is going to happen, and we have to see how that's going to happen. So I did a structural buckling analysis. I couldn't do this one before because you actually need an educational license to do it, because it takes like 4 times as long, and so it costs more credits. But now let me look at if I look at my structural buckling, did we get any? I did a structural buckling analysis, so I just did that, loaded up the test in the same way. But then I have a look at my results, and over here we have, when we do the buckling analysis, it finds modes. Right, so what it does is it keeps doing it all the situations. When you bend that metal ruler, the computer doesn't know if when you push down that metal ruler, if it's going to bend and flex to the left, or bend and flex to the right, or even twist. Or like, imagine if you're crushing a soda can, right? You don't know the exact orientation that the can is going to be crushed with. You know it is going to crush, but is it going to crush and crumple to the left, crumple to the right? You don't know. So what it does is it tries to do different, it puts in minor errors into the force and like other factors to try to see where, how it's going to deform. And usually when it's buckling, it's like it's happening exponentially. So if we have a look at the simulation we had over here, and I started this simulation at 220, and it took 15 minutes to be done, while the static stress only takes 2 minutes to be done, so it takes a lot more time. But over here we see, what do we have? Apparently buckling is only by displacement. If we look over here, this is the mode 1 of failure. So if we look at if we put a weight on this particular crane over here, we can see what's happening in this case over here. The crane is, or the lifting device, when you're going to put a load on it, it's instantly flinging to the left. Or let's just assume in this view that direction is to the left, it's going to the left. If we compared it to the original one, it stayed exactly vertical. And this kind of makes sense of how you imagine this would happen if you're trying to hold up an object. It can also fall to the left and right. We can also look at, and this particular load case, it says over here, happens at 1.995 times the load. So I put down 250 newtons, which is 25 kilos approximately if we assume gravity is 10. So at about double that, at about 50, it's going to start to fall to the left and right. We can also look at, there's a buckling in the negative load case, which means if the load was going up, right, it would buckle this way. And hopefully that would kind of make sense if you are bending that up. These two, so this is the force we have over here is defined as this arrow going down over here. But if we had a negative force on it, so it tries to test for all examples of the load case plus or minus, we would have this buckling over here. And then let's look at another load case, let's say 2.45 going down. In this particular case over here, we're going to get these members over here to buckle. So what this buckling simulation has done, and I'm not sure where it determines what a buckling is. I think there's a particular equation that determines the probability of something will buckle at a certain force for a bunch of boundary conditions, and so it just assumes that. So realistically, we know our crane's not going to have a negative load, right? But we know our lifting device will have a load at twice. That means you're getting to like 50 kilos. And then if we go, so if we get up to that particular load, we know that our crane could go, it could fail into the left, and symmetrically it could also fail to the right as well. But we know once we get into twice our loads that we put in this scenario, then if we go to 2.5 times or 2.4 times, which is what? That's like not 75, like something around 60-ish, 65 kilos. The bottom two supports will start to buckle. And remember, this is still in an ideal scenario in that we have these pins over here, this is locked in, and these over here are pinned. In the real world, where there are pin joints, there's more likely to be buckling in that area because it gives it an extra degree of freedom. And you can do this simulation on Fusion 360 to check the buckling. Again, it takes 3 or 4 times as long, so this is definitely one of those simulations where you want to run it and do it overnight, do it like when you don't need to. Well, it doesn't really matter about accessing your computer, but you know you're not going to get it back for like an hour or something, depending on how complicated your design. This is a very, very simple design. And just for fun, while you are doing your work for this lesson, I'm going to try doing the structural buckling on the more complicated design we have to see how that looks out. We might get some cool modes or something like that. Alright, I'm coming back from a pause. I went to run this more complicated design. You may have seen this one before. Some things that I changed, I didn't bother getting all the individual rivets to work in this. I just made it automatically simulate if there were 2 surfaces next to each other to connect those 2 surfaces. For the sake of buckling, you very rarely have anything of relevance in buckling close to joints, because that's where the members are like thick. You have most of your buckling in the long members. This particular job took about 30 minutes to run, and I made it run because if you go to manage, you can actually choose how many, sorry, wrong one. If we go to structural buckling, you can go there and you can press the manage button once this unfreezes itself. You can press the manage button and you can choose how many different modes you're going to buckle. So I picked 5, so we've got 5 cases over here. And let's look, and I also changed it. This load over here is 500 newtons, so it's twice as much as the other one. I just wanted to see some extreme cases. So if we look here, this over here says this is going to buckle. It's obviously not going to look. It's not obviously not going to look that bad. This is over the top displacement, just so it can you can demonstrate how it's going to buckle. But if we put load down over here, we can expect that part to buckle, and that's at about 13 times, so 13 or 13 and a half times 50 kilos. If we look at case 15, we see this particular member over here is going to buckle, so it's going to go like wide. And then let's look at case 3. We're going to get, that's very similar, and case 4. So in this particular member, this over here is a very, very overproduced structure for buckling. Right, as you see here, the earliest case is 13 times 50 kilos. So 15 times 13, just going to get my calculator, is 674 kilos, which is way past our design case. But when we were doing this simulation before, we were finding that anywhere where there's the bolts connected to the material, that's going to fail at about 50 kilos. So for this particular design, we care less about, this is not going to worry about buckling, we'll worry about more about loads at the individual joint ends. So if I was to change this design, I could take out a whole bunch of these extra members in the middle here, and find a way to give like maybe put in a double thickness over here at the end, because where the pop rivet is where there's going to be more failure compared to the buckling, because this one is 15. When we're not going to see anything more interesting, because these pieces would fail before anything else in our design here. Right, so that's it. That's what we've learnt from our buckling. See you next time.